All right, so today we were going to start to go through Exam 3, Page 1 from the Spring 2018 semester. This is covering chapters 5 and 6. Chapter 5 is the alkenes, and Chapter 6 is the addition reactions. And so we're going to be going through the exam for that. All right, so first page here. Just kind of let me zoom out here for a second so we can see what we're looking at. There it is. All right, so we just got a series of questions, and the directions say, to provide the best answers, to fill in any of the empty boxes. We may not have to use every box. We need to draw the major organic product or products. So let's go through and start to take a look at this and see where we can come up with our answers. So, okay, first thing, if we'll notice, right, we're in chapters 5 and 6, so we're exclusively dealing with the reactions with alkenes, right? That's where the magic happens. And so we need to pay attention to that. In this first one, we got an alkene, right? We got H2O, H2SO4. Remember, this is the same as H3O plus, right? So we're just doing an acid catalyzed hydration, right? So we're doing acid catalyzed hydration. Whoops, acid catalyzed. So my goodness, can't spell, sorry. Acid catalyzed hydration. Remember, if we're using an acid, typically we end up forming a carbocation along the way. We typically use the acid in the first step, right? If we have a carbocation, we have to pay attention to shifts and rearrangements. We have to pay attention to our racemate, right? If a racemic mixture ends up getting formed. So a lot of things go into just that simple bullet point of a carbocation getting formed. It doesn't ask us to show the mechanism for these, right? We just need to basically do the flashcard, so to speak, get from the beginning to the end. So keeping all that in mind, we're going to add an alcohol, right? This adds, right, an H and an OH, right? That's what the acid catalyzed hydration does. And we add the OH. It's a Markovnikov addition, right? Right, so Markovnikov addition, that means we add the OH to the more substituted side or wherever the most stable carbocation gets formed, okay? And so if we're looking at here, we've got our choice of red and we've got our choice of black carbon there that's involved in the double bond. We notice that the red carbon is tertiary, right? So tertiary there versus the black one's primary. It's a terminal alkene is another way of saying it there, right? So we're going to add our OH to the most substituted side, right? There's our carbons, and so we're going to bring in our OH, and there it is. Okay. Pretty simple to begin with. Add your OH to the most substituted side. Now, it's not a chiral center there, so we don't have to worry about R versus S or the racemic mixture, right? We can just show one example there. Okay. Moving on down to the next question, we got HBr. So here we have our hydrohalogenation. Right? So we're adding a hydro and our halogenation, right? So we're adding the H and the Br. Again, it's a carbocation, right? Markovnikov addition. Okay, so a lot of the same bullet points that I mentioned for the first one there. Again, right? We got red, we got black. Red is tertiary, black is secondary there. So we're going to be adding our Br to the most substituted side, right? So let's draw in our alkyl chain, okay? And so we'll just drop our Br on the most substituted carbon there, all right? Don't have to worry about rearrangements. We've got a tertiary in this case, so we're not going to do any kind of weird shifts or anything. Okay. All right. Okay, so here we have our halogenation. Right? Remember, whenever we see our Cl2 or Br2, right? Whenever we see those, we're doing a halogenation. That means we're going to be adding a bromine and a bromine. Okay, this is our SUMO mechanism. Right, our SUMO mechanism, anti-addition. Right. There's no water here, so we don't have to worry about the halohydrin formation, right? Anti-addition, there's no carbocation. Remember, that's what the SUMO mechanism talks about there, right? We have that bromonium intermediate, right? We have a partial cation that gets formed, but no rearrangements yet, right? So we're not doing any rearrangements yet with that SUMO mechanism. So we're adding a bromine across our double bond, right? We're adding a bromine across our double bond to the red and to the black carbon there. And it is anti-addition, right? So that means we are going to be adding one wedge, one dash, right? So we add a bromine, and we could just as easily add them in the other direction also, right? We're wedge and dash. Okay. Now for this next one, there's a couple of answers that we can have. I'm just going to show you an example here, right, of what we can do. If we use this, right, and then we can do our oxymercuration. So mercury 2 acetate with some water. That's our oxymercuration, and then our demercuration is done with NaBH4, right? That would be perfectly fine for us to do that. We could also do our hydroboration, oxidation, and start from that alkene right there. So either one of those two will get to that answer. Here we see a syn, meaning on the same side, diol, our syn-diol formation. There's only one reaction that we know of so far to do this, and that is our osmium tetroxide reaction. And if we use that osmium tetroxide on an alkene, right? There it is. You could put a solvent down there if you wanted to. You don't have to, right? This is what makes the reaction work, right? There are some other things that go into this, but the osmium tetroxide is what I wanted you guys to pay attention to. Ozanalysis here, right? Here's our snip, slide, and slap. So we're going to snip our alkenes. We're going to slide them apart, right? So we snipped, we slid, and then we just slap some oxygens in place. And there's our answer for that. Snip, slide, and slap. All right, so I'll zoom out here so you guys can get the final picture for everything if you want. Remember, no mechanisms here, just going through products to answers and fill in any of the blanks in between there.